Okay, put your cell phones away. They should have that one out anyways, but I've seen some on some laps. Okay, so if it's on your lap, put it away. Okay, don't let it distract you from the last thing you need to learn. Okay, once again, I know it may feel like a second, right? Like, I only looked at it for a second. Okay, but the research shows that that 1 second of moving your focus away from what you're trying to learn can take your brain 20 minutes to fully get back to where it was before. Okay, like it's not a small detour you're causing yourself when you're trying to learn something new, and especially when that something new isn't like the easiest thing in the world, right? Let your brain have that chance to develop those pathways, right, and build those strong connections, okay? All right, so last time we talked about fission. Can anybody, you can look at your notes, but anyone in their own words, so not the words of your notes, but in your own words, can you remind us what the process of fission is? We did the fusion star activity, not fusion. I mean, yes, fusion. We talked about fusion, we didn't talk about fission. Yeah. Sorry. Correct my voice here. Can someone remind us what the process of fusion is? Caleb, go ahead.
Fusing atoms together.
Fusing atoms together, and then what happens?
Releases energy.
Good. So tons of energy comes out. Once again, that's the energy of the sun, and what's created?
Another atom.
Good. They turn into something new because the literal protons combine. Right? Now, once again, this process happens naturally in the stars and in the sun, all the time going on. Humans can do this process. That's how we've created the man-made elements. We have huge devices called atom smashers, are their nickname, aka particle accelerators. And they send these particles through these massive long tubes that are like miles long. They're underground, mile-long tubes, so they can build up enough speed and energy, and then they smash them together, hope they stick, and that's how you make a new atom, new element, right? Good, thank you, Caleb. Have a smiley face for us, but fusion. Once again, to help you not mix up the word fusion, think fuse, right, coming together. So let's talk about the opposite and talk about fission. So fission is the process of taking a nucleus and causing it to split into two separate atoms. So once again, pretty much the opposite of fission. Or fusion, sorry, okay? So in nuclear fission, it involves splitting one large, heavy nucleus into two or more. Now, this process doesn't just happen on its own, okay? This is something that is forced to happen, okay? Nuclear decay, alpha, beta, those just happen on their own. We can't control them. They just happen because they're trying to become stable. This takes something that's unstable and then almost pushes it over the edge, and so then it just like rips apart. Okay, this is the idea of splitting an atom. Okay, the way that it works is by adding a neutron to an already unstable nucleus. Right, it's already unstable, and then you throw another neutron into it, and that neutron almost acts like a little knife, splits it apart, and that's fission. Okay, with this process of fission, the thing is it also has an immense amount of energy that results when it happens because of that nuclear binding energy, right? All those rubber bands, when the atom splits, also start flying out, releasing energy. What happens, though, is those then can run into other atoms nearby, because if I had a sample of uranium, right, one sample in my hand is like zillions, more than zillions of atoms. It starts with one atom splitting, but then it's a domino effect. So we're going to watch a little simulation with some ping pong balls and mousetraps that kind of simulate this idea of what we mean by like a domino effect. Okay.
All right. Teachers love mousetraps because they're a great lesson in potential and kinetic energy. So potential is energy that could happen.
Yeah.
And then kinetic energy is moving energy.
Okay.
So if we set this mousetrap.
Yeah.
And there we go. And I'm going to put a ping pong ball on it. Carefully.
Because mice love ping pong balls?
Well, it's a good demonstration. So when this flips, it'll take all that energy it's storing and release it.
Yeah.
So I'm going to drop this on there, and then we're going to see if we can get that ping pong ball to fly.
Okay.
All right, so here we go. Ready, and there we go. That's a good 30 feet.
Okay. That was a crappy trick, by the way. I mean, that's nothing like the foam already. We should have started with that probably.
Well, we got the idea. That's a lot of energy in one mousetrap.
Yeah.
But what if we picked it up just a little bit and tried it with a couple
10 million mousetraps?
Well, we'll start with this. Wow.
That's beautiful.
There it is. You have an amazing prop department here.
Yeah, boy, they must hate you right now.
All right,
That's incredible.
what we're going to do is we're going to trip this by just throwing some ping pong balls in. We'll see
Okay.
how many it takes to actually start it, and then we'll see if it can release energy.
Should we throw them all at once or throw them individually?
Let's start with one and go from there.
Okay, all right.
So it's also actually a model for Newton's third law. It's a model for how fission works. It's really okay.
Okay, nothing happened?
No. You have a law.
Oh, you got a lot. Okay, all right.
Go ahead.
Let me look. Oh! Thank you, Science Bob. We'll be right back.
All right. Teachers love mousetrap.
Okay, so that's the idea behind fission in terms of a lot of energy, similar to fusion. If only one atom fuses, it's not going to be that much. I mean, it is a lot of energy, but for one atom. But what we see is a whole bunch of atoms in the sun fusing together. The same thing in a nuclear bomb. A nuclear bomb isn't a single atom splitting. It starts with one, and then it causes that domino effect of neutrons flying out, resulting in continue, and then that's where all that energy comes out of. Okay? So we're going to do a little simulation, and now the point of this, it's a little strange. But it's something I've done over the years, and it really sticks with students, and so that's why I continue to do it, because I hope you want to find things that will help stick with you. So we're going to use a simulation, and we're going to drop some nuclear bombs on Skyridge High School.
Yeah.
Now, the reason why I picked Skyridge High School is not because I don't like it here. I like it a lot. But I want you to understand the area, and because you're familiar with this area, it will make a lot more sense of like how big of a blast it was, versus if we were to pick like some random desert, you don't know how wide that truly is, right? Your understanding of how big it is, it will be much better, okay? All right, so we're gonna go to this here real quick. All right, so let's find Lehigh, Utah. Then let's zoom in and find us. All right, this building right here. Okay. Oh, I gotta bring our little thing over there. Okay. So to compare, once again, what I want you to pay attention to is the energy. Okay, to recognize the differences between different types of energy and the process that's going on. So the first type of one I'm going to do is a chemical reaction explosion. Okay, in a chemical reaction, at the molecular level, it's all about the electrons. The electrons move, the Legos stack differently, and energy results. Okay, chemical reaction, the Legos are all still there, they've just rearranged themselves because of the electrons. Okay, so this first one we're going to look at is a chemical reaction. Okay, AKA like TNT is like a chemical explosion. Okay, typically most bombs are a chemical explosion. Okay, so here we go. Okay, are you ready? 1, 2, 3. Now the different colors indicate like differences of where like the just like radiation, not radiation, but like blast radius, right? That would feel the blast radius. So, I mean, can be pretty detrimental, right? Like the school's gone. Maybe if you live super close to Skyridge, your house might be in trouble. Okay. Once again, notice we're going to compare and contrast here. Okay. Okay. So now, so that one was a chemical example. This one is now going to be a fission explosion. Okay, so this is using the process of fission. So what happens in fission? what are the atoms doing? Splitting. Right, so this is a process. If you split an atom, domino effect, split a bunch of atoms, the energy that comes out in that process. Okay? Alright, everybody ready? So once again, kind of have an image of the first one to compare to this one.
Yeah, you're good.
Okay.
I don't think you do.
You still okay?
No, my program, right?
Okay, so now this one is a nuclear explosion, so there's a few different colors because of it. The inner radius is the fireball radius. The red goes to the heavy blast damage. Green is you're still in the radiation. You may not die instantly, but you'll probably die of cancer eventually. This is blast damage radius. This is thermal radiation, meaning like 3rd-degree burns can happen within that zone. And then still some sort of blast radius. So, once again, comparing chemical to fission, how's the energy compare? Like, way, way different, right? There's so much more energy when you start messing with the nucleus of atoms. Okay? Alright, now the last one, so we've done a chemical reaction, fission, now we're going to do a fusion bomb. Okay, so what happens in the process of fusion? Okay, everybody ready? Okay, so show me with your hands what happens in fusion. If your hands are, there you go. Come together, right, creating a big one. Okay, all right, here we go. 3, 2, 1. Okay, so for those that maybe can't read the small writing, this is Nephi, Utah. Okay, and up there it goes all the way to Ogden. Okay, so fission versus fusion, which one has more energy? Fusion, like major difference, right? Like the other one was a lot still, but it didn't even like, you know, like this one's almost all of Utah, right? Now, obviously, this is like a very negative side of how the energy can be used. The fission one I showed you is actually the same size of bomb that was dropped during World War II. Fusion bombs have never been used, so there's only, in case you're unaware in the history, there's only been 2 times in history where we have used nuclear bombs, and it was the US in World War II. Outside of that, they've never been used on people. Now, they have been tested in a variety of different ways, and these ones, this one has been tested. There's actually a video on YouTube of you can watch them drop it. They have to actually slow the descent of the bomb with the parachute so the airplane, the jet, has time to get out of the blast radius before it explodes. Right, so they have to like, don't let it explode too soon. But they dropped it in like the barren deserts of Russia, because that's who dropped it. So these ones, the fusion bombs have never been used, and obviously these are like kind of scary and like not positive ways in which it's used. On the reverse side, we're not talking about it in this unit, but in another unit up ahead, we'll talk about the ways in which actually this can be used in a positive way for energy we need, in producing electrical energy, powering our towns, our cities, our country, with the possibility of this energy, right? If you can harness that energy instead of an explosion and use it in a positive way, right? Like it can actually be a very cheap energy source and can actually be quite clean. Because if you'll notice in this one, does anyone notice what color is not part of the blast that was in the other one? Yeah, there's no radiation. Fusion doesn't release radiation. Unlike fission, fission releases a lot of toxic radiation, but fusion is very clean. We just don't quite know how to harness it yet. But yeah, Jean.
So with fission, does it happen naturally, or do we have to put the...
We have to have, yeah, so it's because it needs a lot of force, because we're sending another neutron into the nucleus, right? And it needs a ton of force, and so it's something that inside like a nuclear bomb, it like does that.
Okay.
It shoots a neutron at an unstable
So
nucleus.
then, once that happens, it happens to all of the atoms around it?
Because then, as that one then goes off, it kind of then sets the others off like the mousetrap idea. Does that make sense? Yeah, good question. And that's the same thing like in a nuclear power plant, you have control rods that are doing the same thing where they're sending in the neutrons to cause the fission to happen. Okay? Now what's cool about this process, once again, is we see, oh, I don't know why I did that. Okay? We see it based on the data of the elements in the universe. Right? This idea of it all starting with hydrogen matches what we find in that there are very few of the very big elements because those aren't created until the star explodes, when most of the universe is hydrogen and helium, because they're the most basic Legos, the building blocks of what we have, which supports the idea of the Big Bang. So it's kind of cool to see like how that matches up. Any questions on fission or fusion? There's one more thing we'll look at here with the graph. So. Okay, is everybody good on this slide if I go to the next one? Okay, so here's a graph. This is the distribution of elements in the universe. So this is, blue is hydrogen, so once again, and red, pinkish is helium. So most of the universe are those two things, which once again makes sense because everything else had to be created from them. So obviously you'd have the most of the simplest one. Okay, now coming back to this graph that we've looked at before, this graph with the idea of nuclear binding energy can help us predict whether something is more likely to go through fusion to become stable or through fission to become stable. Does anyone remember what was the maximum element on this graph that we identified? Iron, right? Iron was that last piece in the star, and that's the peak, and that's the dividing line. Okay, is that line drawn on your paper? On your notes already? Perfect. So at that line, everything before it is more likely to go through fusion. Now once again, fusion can't happen on its own either. Okay, not like alpha, beta, those just happen. Okay, fusion, you need a lot of energy and heat for it to happen, but if that's available, these things would fuse. It's very rare to get them to go through fission because they're so small, the likelihood of just splitting apart doesn't really happen. But everything above iron is less likely to go through fusion and much more likely to go through fission. Once again, because they're kind of all trying to get to that perfect stability right there in the middle. Okay? Questions on that? Yeah, over.
Usually it's very likely that don't go through fission instead of fusion. Can it still go through fusion?
You know, in the world of science, I'm very cautious to say like never, because under the right, like if you controlled it in a lab setting, maybe you could force it to happen, but it would be very hard for it to. Most likely, like sulfur, right? The sulfur comes before iron, right? So sulfur only has 16 protons. Most likely, if I sent a neutron into this, trying to get it through fission, most likely it would just take the neutron in, maybe be unstable, but not so unstable it's gonna rip in half. It probably would then maybe just go through like alpha decay or beta decay to become stable. So, does that make sense? Yeah, great question. Have a smiley face for that. Any other questions on this? Yeah, Jean.
So just the ones on this side, they still don't have it by themselves.
Correct. Yeah, it's just like if I was looking for something like I'm like, okay, I want to do something, have it go through fission, you definitely wouldn't want to pick something on the other side because that would like never happen.
Yeah.
So yeah. But the same thing, none of this fission and fusion does not naturally happen on its own outside of the stars and the sun, right? Because that just already has enough heat and energy for it. But you're not just going to have an atom randomly split and a nuclear bomb goes off on its own, right? It's not going to happen. So, any other questions?
What's, I don't even know if you use that word, constituents?
I'm not finding, where's the word at?
It's in the first paragraph. Is it like constant or something?
Oh, it's just saying parts,
Okay.
like into smaller parts. Fancy word for it. Yeah, thank you for clarifying that word. Yeah, so fission will occur if the nucleus can decrease its energy best by splitting it into smaller parts, is pretty much what it's saying. And then fusion is the idea of them coming together. So, okay, what we're gonna do for a little activity to kind of put this all together, okay? First round, no talking, you have to do it completely on your own, okay? I just want you to use your brain. You can use your notes and what we've learned, okay? Here's your task. I'm going to give you a little container of Play-Doh, okay? Your job is to imagine that you are now the teacher and you are teaching someone who hasn't learned about fission, fusion, or nuclear decay, and you're going to model somehow with Play-Doh to teach them those three things. Okay, so fission, fusion, and nuclear decay. However you want to model it, but I want some sort of visual for them, okay, of what it is. Okay, so I'm going to give you like 5 or so minutes on your own, so I don't want any talking. Okay, you can talk to me if you want to like run an idea by me or you have a question. Okay, but no talking to your neighbors. Come up with it, and then I'm going to pair you up with somebody, and you're going to teach them with your model. Questions on your objective? Once again, it's coming back to our can you differentiate between fission, fusion, and nuclear decay. So those are the 3 things you need to model. Okay, any questions before I pass them out? Okay, now disclaimer, I haven't opened these since last school year, so if you get one that's dried out, let me know and I'll trade you. We try to seal them up really good at the end of every year, but you know, it's been a long time. So if it's dried out and you need a new Play-Doh, let me know. If you don't like your color, you can trade with someone around you. They get smaller as the mass gets bigger. I don't know where that one went. And kind of pull it out and play with it for a second to see if it's too dry, because sometimes once you like move it around, it will then be okay. But if it's like crumbly on you, let me know. We'll get you